very important one. This is the Aref Memorial Lecture. I made mention to Hassan Aref in my opening remarks yesterday, but we're very lucky to have Morten Brøns to give this lecture. As I mentioned, he was working with Hassan and had just completed a paper on point vortex dynamics, which was one of Hassan's passions in life, in the weeks before he died. So it's great that we have Morten here, and he's going to talk to us on bilinear relative equilibria of identical point vortices.
Thank you. Thank you very much. So while I do my introduction, I would like to have a little slideshow with pictures of Hassan. I'd like to stay here while I do the introduction. So thank you very much for the invitation here. I'm very pleased to be here. Although the sound. Technology. Is that better? Yeah, great. The background is, of course, a sad one because Hassan passed away in September last year. He should have been here giving a talk, I think, called Vortex Statics Revisited. And I think he would base that on the paper we had submitted just a few weeks before he died. So the talk today will be about, I will give a little overview of Hassan's work, and then I'll turn to our paper. So I think so. Hassan was sitting in his favorite chair with his favorite MacBook and probably doing his favorite pastime, doing vortex dynamics, when he quietly passed away the 9th of September last year. And it was caused by an arterial disruption, I think it's called, and his son Michael had said that it's one of life's little ironies that his father was killed by turbulence, because obviously Hassan's main interest was things that were not quite so turbulent. So, but let's get down to it, and let's see here. Here we are. Yet another few pictures. So this is Hassan with his favorite equation, which I'll discuss in detail later. I've written it over here for reference. So this is taken at a symposium at the Technical University of Denmark, and a IUTAM symposium celebrating 150 years of Helmholtz's paper on vortex dynamics. But I would like to start to sort of review some of Hassan's work, and I think he made a very important contribution to the basics of fluid mechanics with his paper Stirring by Chaotic Advection from 1984, which was written in sort of this period where nonlinear dynamics was gaining new life from chaotic ideas, and what he did was that he realized that you could have very simple fluid flows which could give rise to very complicated mixing. So the simple example he had was 2 point vortices here generating a flow. If both are rotating, you will see a streamlined pattern like this in a steady flow. But you could turn them on and off, turn one on, and then after a little while turn the other on, and then you have this blinking vortex. And even if the flow at any time is very simple, the streamlines are very simple, you get this chaotic mixing here. And Hassan coined the term chaotic advection for this phenomenon here, and it has sort of grown into the fluid mechanics vocabulary and as a fundamental concept of fluid mechanics. His paper here has, as of 8:30 this morning, 1,016 citations. And you see they're still ticking in at a rather constant pace. So even if it's almost 30 years ago, he wrote this paper, it is still a key publication. And obviously this pioneering work was a major part of the reason for giving him the Otto Laporte Award in 2000. Closely related to this is the work on topological fluid mechanics of stirring, and we had some details yesterday by Phil Boylan, so I'm not going to details. The interesting thing is that this work was linking fluid mixing to the Thurston-Nielsen theory of diffeomorphisms of surfaces, and this classification of these mappings into several categories. Some of them are mixing, and some of them are not. Seems to be a very fundamental thing in fluid mechanics, and has certainly given rise to a lot of interesting works after this pioneering paper. So there's an interesting historical comment I would like to mention. So, well, first I would like to say that Hassan was Niels Bohr visiting professor at our university. He spent all the fall terms in 5 years, from 2006 to 2010, at the Technical University of Denmark. And last spring he got the honorary doctor's degree at our university, partly motivated by this work on topological mixing. And one reason this is particularly interesting for us in Denmark is that Nielsen was a Danish professor, and he was a professor at our university. And he was actually even if he was a mathematician, he was a professor of rational mechanics. He wrote a 2-volume textbook on rational mechanics published by Springer in the 40s, I think, 1940s. And he was a very good lecturer, but he never did any research in mechanics whatsoever. So his teaching world and his research world was completely disjoint. So it was particularly satisfying for us at the Technical University of Denmark that you could connect these very abstract ideas with some very concrete fluid mechanics things, which even have engineering perspectives. So that was absolutely great. Maybe Hassan's greatest love was point vortices, motion of point vortices, and he has written very many papers on this topic with very many different aspects of this physical problem here. One thing I would just like to mention here is the point vortices in a periodic strip as a model for wakes behind bluff bodies. Obviously, one of the greatest successes, I think, for point vortex dynamics is von Karman's analysis of the stability of the wake of the cylinder by an infinite array of periodically repeating vortices, where you only had 2 vortices. But clearly you can have more than that, and just adding another vortex gives an extremely rich structure of possible motions. Some of them would move with a constant velocity, so they're sort of steady states, and they would be good models for good representatives for something that could model a wake where you have these clear vortex structures here. And so this is from this paper here, comparing an experimental picture with one of these arrays of periodic vortices with 3 vortices. This is an exotic wake, meaning that it's more complicated than just the normal von Karman wake, and it's created by oscillating the cylinder, and you get pictures like this. And sort of, I think rather than having sort of a complete success in this, Hassan considered this, I think, sort of as a program for understanding vortex streets. So if you sort of take von Karman seriously and say that these point vortex configurations are good model for wakes, you could sort of see how far can you get from this approach to understanding wakes here. And clearly you can go far beyond that and have much more complicated vortex structures here with point vortices. Perhaps you cannot realize all of them from a cylinder, but no matter how complicated you make the motion. So I think one interesting point of this paper is that you should not expect to be able to see any possible wake structure behind the cylinder, but there will be things that are much more complicated than that. I think that's a very interesting program that sort of has not quite finished yet. I was involved in a very in a small but I think very nice little adventure with Hassan a few years ago. Again, if you have point vortices, they move around in the field induced by the others. You could ask about the flow induced in the rest of the fluid by these point vortices. And you may want to know where the stagnation points are. So suppose you have 3 vortices here in a triangle, and they are identical. It's relatively easy to see there must be 2 stagnation points in a flow like this. But where are they? Well, it turns out that there's a following classification. So you take the midpoint of the triangle between the vortices. You take the ellipse, which is inscribed in this triangle, which touches the sides of this point here. It's not quite obvious that such a thing exists, but it does. This has 2 foci, and these are the stagnation points. So this is a special case of what's called Seebeck's theorem, which has been rediscovered many times in mathematics in various disguises. But this gives sort of a very simple geometric classification, which I think Hassan enjoyed very much. We almost reinvented it, but then we found a book called The Geometry of Polynomials, and this theorem was on page 6, so we were a little bit lucky that we didn't have to do the work again. Sometimes if the vortices not have identical strength, you have 3 vortices, you will get other conic sections. Here is a case of a hyperbola, and the foci of that will give the stagnation points. And it actually generalizes to several vortices. Then you have more complex curves, and you will need a little projective geometry. But one thing that was, well, maybe not an obsession, but close to for Hassan, was the question of relative equilibria of point vortices. And this is the main topic of my talk, really. So what do I mean by that? Well, we start with the point vortices. We consider a point vortex as a point in the complex plane. So Z is a complex number. We have n of those, and each of those vortices, they move in the field from the other vortices. So each vortex has a strength gamma, and the length of the velocity field from a vortex is 1 over the distance. And you sort of sum all these contributions. You have to turn this velocity 90 degrees. That is, the I is taking care of that. And then the prime of here means that you should not sum when beta is equal to the alpha here. So you get this set of n complex differential equation for the motion of the vortices moving in the field induced by all the other vortices. So suppose we have this number here. So the weighted positions of the vortices is a constant of motion. So you may choose your coordinate system such that the center of vorticity is at the origin. And you may ask yourself, is it possible to have a configuration of vortices that is rotating as a solid body with a constant angular velocity, meaning that you would have this relation here? Well, that's very easy. You simply plug it into a differential equation, and you get that equation out of it. If all the vortices are identical, and that's the only thing I'll be talking about today, all the gammas are identical, you can scale the time such that you get this equation here for the position of the vortice. So you have n equations in n complex variables, which is a set of algebraic but nonlinear equations of this form here. And this is what you want to solve if you want to know how these relative equilibria are how they are placed in the complex plane. So this seems rather innocent, this equation here, but it turns out to be a quite complex problem. Just for motivation, do you see stuff like this in nature? Well, I think you do. There's a classic example with vortices in superfluid helium-2. And there's a classic picture here of some of these vortices here, which are sort of vortex crystals. So they are sort of fixed structures, possibly rotating in space. And yesterday, we also, in Okitani's talk, we had a brief discussion of these structures as well. Or you may have several vortex structures get generated in different ways. So you have something like a tripolar vortex like this, with sort of fixed structure which is rotating and translating through the fluid. So certainly these objects do exist. What do we know about that, about the solution to this problem? Well, we know that if we place all of them on a line, that's certainly possible, then they will be sitting in the zeroth roots of the nth Hermite polynomial. So I'll return to that in a moment. You can also place them in a regular n-gon. You can also place them in certain nested polygons. And quite a while ago, Campbell and Sif made the Los Alamos catalog, which was a numerical investigation of possible stable states. And they found a lot of those with up to n equal to 30 vortices. And I think it's still believed that they got all of them, all the stable ones. There are a lot of unstable ones, but the method didn't allow them to find that. That was not their interest. So all of this is nice, but there are also some very complicated ones. And Hassan has a beautiful paper with Weinstein in Nature in 1998, where they find new solutions by a very nice trick. First, they will start with a configuration with n vortices and try to find a relative equilibrium with one vortex more than that. So first they place the n vortices in a relative equilibrium, and then they compute, by solving this equation for Z, all the co-rotating points. So there will be points that are stagnation points in the rest system of this equilibrium system. And in that point, you place a little vortex with strength epsilon. And then you take this combined system, which with n plus 1 vortices, and try to find a new equilibrium position. So the little one will only disturb the n vortices a little bit, so it's easy to, by Newton's method, to find the new equilibrium. And then you slowly grow epsilon up to 1, and then you, by homotopy, you may find a new equilibrium configuration. You may also not be successful, but in many cases you are. And by this method, they found a lot of the well-known patterns, but also some very strange ones, which has no apparent symmetry at all. And I think we had this morning a brief discussion of this, exactly this picture. So this is a numerical result, which is a little bit surprising, and it gets even worse in some sense. So here's a well-known analytical solution, a centered double ring. So you have these three vortices are lying on a circle, and the outer ones are also. And you know that one analytically, and the coordinates of the vortices are at these points here. So you may want to solve these equations numerically, and you may get this solution here, which is depicted up here, and to the naked eye they look identical. But if you look at the numbers, there are little differences here. They are not completely in the same spot, and you may want to say, well, that's probably only numerical error. But that turns out not to be the case. And here's an even more convincing example. So here's some very large systems with very many vortices, where there are some analytically known symmetric configurations, which are marked by the black spots, and there are some numerically found equilibrium states with the white spots. And you see they're slightly off the symmetric cases. So the original computations were done by Dirksen and Aref with double precision computations, but being a little nervous that they made a mistake, they repeated it with 300 digits, and to make sure that everything was okay. And this sort of was confirmed that these slightly asymmetric states, they also exist. It appears that there are similar situation in celestial mechanics, so maybe it's even correct. So the problem of solving this equation here is indeed a complex one. This is then one contribution to this problem, which is a paper we submitted well, you see just shortly before Hassan died, and I'll explain what it means. I will just say a little bit about the background. So at one meeting at the APS Division of Fluid Mechanics meeting, Hassan was giving a talk on some of the on this relative equilibria thing, and he ended by saying, "Could someone please help me? I'm spending way too much time on this." And it was sort of obvious that you would need new ideas to go on. And looking at this problem, you would say, well, you would need some algebra. I mean, this is not an analytic problem. It's clearly should be some algebra hidden in this one. So while Hassan was a Niels Bohr visiting professor at our university, he gave a talk, and one of our young algebraists, Peter Behlen, he took the bait, and we started a collaboration on this problem here. It turns out that no algebra whatsoever turns up. It is all analysis, but since Peter is a very accomplished analyst as well, we succeeded in getting something new, I think. So before I go to the case we'll consider in the paper, let me just go through briefly through a derivation of this case where you have n vortices on the x-axis, which I claimed before were placed in the zeros of the nth Hermite function. And the way to do that is to define a generating polynomial from the point vortices. So the point vortices are placed at the points x alpha, and you define a polynomial where the roots are exactly at the point vortices. And we'll derive a differential equation for this function p in the following way. First, we differentiate it once, so this product differentiated gives us sum here. You can write it in this way. You differentiate once more by standard rules. You apply the derivative you had in above here and plug that in here. You get this one here. So you see you will have in this sum a lot of products of 1 x minus x alpha, x minus x beta, but you will those where the two are identical are not there. So I will write that in this form, where the prime now means that you exclude the one where alpha is equal to beta. You make partial fraction expansion of that, you get this one. And you reshuffle that sum a little bit, taking together the index with alpha beta and beta alpha, and you can easily see, you can write it in this form here. And if you then first the inner sum, you first fix alpha and then sum over beta, and then know you have a relative equilibrium, then the x alphas fulfill this equation here. If you plug that into the inner sum, you only get a single sum over the alphas, and you substitute the sum on the left, on the right with the x alpha on the left. You get this one, and the rewriting is doing this, and finally you end with this expression here. So by these elementary operations, you will get a differential equation where p double prime is equal to 2p prime minus 2n p of x. And this is exactly Hermite's equation of order n for this polynomial p. And the solution, there are polynomial solutions, of course, the Hermite polynomials, and obviously then the vortices are placed in the roots of this polynomial here. That's an old result by Stilches in 1885.
It's got to be good. That's linear constant coefficient, the way you've got it written now.
There must be an x missing somewhere. You're right. Yes. No, it does not have constant coefficients. You're right. We'll sort that out later. Right, so that's all very nice. So this gives an approach to solving this problem, to finding this generating polynomials. And what is exactly this bilinear thing we will be considering? Well, the bilinear configuration is one where you have a number of vortices on the x-axis and a number of vortices on the y-axis, or on some of the real axis and some of the on the imaginary axis. So you will have two orthogonal lines where the vortices are placed. So this is what we mean by bilinear configuration. So you will have little n vortices on the x-axis placed at these points here, and you will have m vortices on the y-axis, on the imaginary axis, placed at these points here. And corresponding to those configurations, you define two generating polynomials which have exactly these points as the roots in this way. So you have two generating polynomials here. Then by arguments similar to the ones I showed you before, slightly more complicated, you can derive this equation here, which is sort of I could call it a generalized Emit equation. So it's obviously an equation where both the polynomial p and q appear. It's bilinear. It's linear in p. It's linear in q. And the idea is to analyze the solutions of this equation and try to see if from analyzing this you could find some new equilibrium positions. Assuming you have vortices at this point, you can show that these polynomials fulfill this equation. Suppose you have polynomial solutions to this equation here. Will the roots of those represent relative equilibrium position of vortices? That's not necessarily true, unfortunately. But the following holds. If you can find a polynomial of degree n, the right degree n, with n distinct real roots, simple roots, and similarly you have a polynomial of degree m also with distant imaginary roots, and they fulfill this equation here, then these roots represent a vortex system in relative equilibrium. So you may fail in the sense that you have double roots of the polynomials. You may fail in the sense that this polynomial will have complex roots and this one will have real roots. In that case, you're in trouble, and the solutions may not represent a vortex equilibrium. I'll show an example of that a little later. Okay, so let's see how that works. Here's the equation again. And so the simplest case is, of course, that they are all on the real axis. Then you recover Emit's equation. And we're back to the case where they're on a line. Then you could think you had one vortex on the imaginary axis. Well, that's not possible because we had the center of vorticity at the origin. So that means that this sum has to be 0. So you cannot have just one vortex of the real axis. That's not possible. Okay, but you could have two vortices of the real axis. And in that case, the polynomial will have to look like this because, again, due to the fact that the center of vorticity is at the origin, the two vortices must be symmetrically placed at the imaginary axis. So you will have this polynomial here with some placed at plus minus I times eta. And so I'll go through some examples with a growing number of vortices on the real axis. So if you have two vortices on the real axis, you will have this polynomial here, placed as plus minus psi. Again, they are symmetrically placed due to the similar relation for the x-coordinates due to the center of vorticity being at the origin. So you plug these two into the differential equation, you get this second degree polynomial. It has to be the 0 polynomial for all values of z. And then you easily see that that requires psi and eta to be 3/2, and you will have vortices in a square. Okay, let's turn up the number of vortices on the real axis, and you get a polynomial like this. What about the second order term? It's not there because the coefficient to a second order term in a polynomial is minus the sum of the roots, and the sum of the roots has to be 0 according to the center of vorticity being at the origin. So there's no term of second degree here, but there are some unknown coefficients here. Well, you plug that into to the differential equation together with the q. You do a little computation, you get this. You see that A0 has to be 0, and then you easily find that A1 is minus eta squared, which is minus 5/2. So you have vortices in a center square. So you still have a vortex at the origin and then symmetrically placed on the real and imaginary axis. So let's get a little more complicated. With 4 vortexes on the real axis, still 2 on the imaginary axis, You take the polynomial, you plug into the differential equation, collect terms of the same order, and then you get a series of equations because these coefficients will have to be 0. And you will see that these equations, they are linear in these coefficients of the polynomial p. So they are easy to solve. They will be solved in terms of this parameter eta, which represents where the imaginary vortex, so to speak, is placed. But you will get a solution like this. And then you will have a final equation which will give you this relation here. If you take that one out, knowing the other solutions, the solutions for the a's, you'll get this equation here for the eta. Eta square has to be positive, of course, and there's only one solution, which is this one. Having that, you can compute the a's, and then you will get these vortex positions here, and you will get this configuration up here. Okay, just to show that you can go on with this forever. Well, maybe I'll skip that one. The arguments are exactly as before, with 7 vortices on the x-axis. You will find exactly one possible configuration for the 2 vortices on the imaginary axis, and having that, you will find exactly the right number of roots for p on the real axis, and you will have an equilibrium, relative equilibrium position here. So to summarize this, we fix the number of vortices to 2 on the imaginary axis, and what we have found sort of experimentally until now is that for any n you can find a unique position of these 2 imaginary vortices, or on the vortices on the imaginary axis, such that you do get a vortex configuration in relative equilibrium. And the first ones you can easily compute analytically. Then you get some quite high degree polynomials. You can only get it numerically. The a's are the eta squares, so these are positive numbers. And you see you get this very nice correlation with the number of vortices on the real axis, which indicate that this an is growing linearly with n. And it does indeed, but I'll return to that later. Just to show you that this does not always work, here's a situation with 4 vortices on the imaginary axis. And let's try to find 5 vortices on the real axis. You can make some arguments by computing some moments that say that if you have 4 vortices, they have to be symmetrically placed. So you will get a Q polynomial of this type here. You get a P polynomial of this type here. You do the same procedure, plug that in, collect terms of same order in Z, and so on. It turns out to be easy to introduce these 2 parameters rather than the etas, the alpha and the beta, and you get some equations of this type here. Again, they are linear in the coefficients a. And you can compute the coefficients, the a coefficients from the alpha and the beta. You get some other equations where you only have the alpha and the beta, and you are allowed a little bit of luck, I think, because one of these equations factors out. So you can easily see there are 2 solutions. Either beta is equal to 9, and tracing backwards, you find the polynomial p having this form here, so that will be a double squared configuration with 1 vortex in the center. But there's also another solution here where this one would be equal to 0. And I've written the equations once more up here. And I make this factor equal to 0. Then I get these values of alpha and beta. I remember what they were in terms of the vortices on the imaginary axis. And I get the following numbers here. And everything is fine. I get this polynomial p. The only problem is that this polynomial p has 2 imaginary roots. And you could think that, well, I mean, they're purely imaginary, so you could think that, well, perhaps that's okay. Perhaps there's some, maybe they really count as vortices on the imaginary axis, but you can plug it into the regional equation, this one over here, and see if it's okay, and it's not. So these solutions do not represent a relative equilibrium of vortices. So this approach with the polynomials, it has some limitations. You may get some false solutions. if you go to the situations where the vortices are symmetrically placed on the imaginary axis, so like this one here. That's not necessary, but let's do that. If you have 2 or 4 vortices on the imaginary axis, there are some moment arguments that say, well, that's the only possibility. But in general, that may not be the case, but let's do that, because then we can prove a lot of things. Here's our generalized Hermite equation again. We can prove that the polynomial solution, the P, so Q is given, I'm looking for the P. It has the right degree. All the roots are simple. There are no common zero, that's good. You can even say that P is even if n is even, and odd if n is odd. And the zeros of P are either real or pair of a complex conjugate pair. These ones are not so good, but we may have to live with them. And if you have one solution, well, the only other solutions are proportional to that. And if you have an even number of vortices, then certainly the origin is not a even number of vortices on the real axis. The origin is certainly not a vortex position. Okay, so I'll not go through the proof of that, but that's a great help. But then really the interesting idea, I think, in this paper comes from this Sturm comparison theorem, which turns out to be most helpful in this. So let me just tell you what that is. So we are in a situation that we have 2 linear differential operators, L1 and L2, and they're given in terms of a function, a common function k, multiplying this derivative here, but 2 different functions R1 and R2 in this way here. We will assume that k is positive. I need some continuity assumptions to make things work. And the theorem is about zeros of solutions to where this operator is equal to 0. So suppose you have a solution to the L1 of u equal to 0, and suppose this has 2 consecutive zeros, x1 and x2. I think I've made a drawing over here. If in the interval between these 2 points, this function up here is larger than this function up here, then every solution where L2 of v is equal to 0 must have a 0 in between. So the zeros of the 2 classes of functions u and v, they are sort of intertwined. There's one in between the other all of the time. Well, let me skip the proof. It's beautiful and very simple, but never mind. This turns out to be most useful here because let's go back to the case we're considering, symmetrically placed vortices on the imaginary axis. This equation here with this given q can be rewritten in this way here. If we, as p, consider the product of these two functions here. Capital P is a product of the 2 generating polynomials. Then you can write it on this Sturm form here. In this case, so this is the k function, and all of this is the R2 function here. You could compare it with the equation where you have dropped this term over here. And it's easy to see that R1 is larger than R2 everywhere. But this is Hermite's equation of order n minus m. So if you have a polynomial solution to that, you certainly do. It's hn minus m, and hn minus m has n minus m zeros. So from this Sturm theorem, we can immediately see that the polynomial p has n minus m minus 1 real zeros, and these are, of course, the zeros of the polynomial little p. Actually, you can do a little better than that, because you can find 3 more roots, because you can find 1 root outside the root on each side, outside the interval of roots of the u function, and there's a parity argument which sort of says that since they come in real or complex conjugate pair, you need at least 1 other real root. So all in all, you will get from this theorem n minus m plus 2 distinct real roots. And so in particular for m equal to 2, you will get exactly n mutually distinct real roots. So that's a case where you have the right number of roots, which then represent a relative equilibrium of vortices. And that's the best result possible, because we saw one example where you indeed did not have more than n minus m plus 2 real roots. This was the case with the 4 vortices on the imaginary axis. Time is running short, so I think I'll skip the proof. There's a simple proof for finding the coefficients in the polynomial little p is found by a linear system. It's easy to see that if you choose the vortex on the imaginary axis correctly, you will get a solution. And again, using the Sturm theory, you can prove uniqueness, because from Sturm you can assume that there are 2 roots, and then it will require there's yet another one, and things don't fit. So this ends out sort of maybe be the primary result of this paper. You do indeed get what was confirmed numerically for low values of n. We can always find n vortices placed on the real axis with 2 vortices on the imaginary axis in a unique way. You can place this in a unique way. That's the result. So just a few words about the asymptotics. On top of an was the now it's getting too fast. An was this eta squared, and you had this very nice relation on top of the points I have drawn this line here. And what we indeed can prove is that an over n is equal to 2 over 3. This 1/2, I don't know. We don't know about that. But just to outline the proof, how does it work? Because again, Sturm is helping us. This limit I'm considering, I call that alpha. And from my basic equation for relative equilibrium, if I take out the 2 imaginary equations that come from the 2 vortices on the imaginary axis, I can get this little one. Okay, I can rewrite it in this form here. What you see here is that, so xmj is the jth root of our polynomial p, corresponding to there being n vortices in total. You can make this little thing here, simple rewrite. You can take the limit as n is going to infinity, then this certainly goes to 2 alpha. And well, the rest you don't know that much about. But since the roots of our polynomial p and the roots of the Hermite polynomial by Sturm's comparison theorem, using that in the right way, comparing with the right Hermite equation, you can sort of replace this limit by this one, where the size are the roots of the nth Hermite polynomial. And this is very nice because we know a lot about that. And we know indeed what such a limit is. There's a theorem by Calogero and Perelomov from 1978, which tells you exactly about the distribution of roots of the nth Hermite polynomial when they're normalized to an interval from -1 to 1. And using that result and plugging into this, you can compute this integral here on the right-hand side, and you find exactly alpha is equal to 2 over 3. So that was basically the results of this paper here. There's more to say. We have said very little about the case where there are more than 2 vortices on the imaginary axis. We said nothing about vortices of different strength. Certainly said nothing about the stability of these configurations. And it seems also that there would be possible to generalize this for multilinear relative equilibria, having vortices on several lines rather than just 2. And what we found, which I think is new in this, certainly Hassan thought that was new, and he knew almost anything about vortex dynamics, was the use of the Sturm comparison theorem. I think that's new. But maybe there's still room for an algebraic approach, and that would be very interesting if you could shed still more light on this one. So let me just finish with a picture of Hassan again. He was a great scientific leader. He was a great friend, a mentor, and a great scientist. It was a personal loss for many of us here. Let me just tell you a little personal story. One night I was sitting and chatting with him, sort of a transatlantic chat. I was sitting at home in Copenhagen. He was in Virginia. We were sending emails back and forth, and it was quite late in Copenhagen. And suddenly Hassan said, "Shouldn't you go to bed?" And of course he was right. It was way beyond my bedtime, and when we said goodnight. So he was a very caring person and a very good friend, and he would even come and talk you in if you needed that. So thank you very much for your attention.
Thank you, Mark, for that beautiful talk.
Thank you.
Yes. Yoshi, questions?
So it may be a naive question, but do you believe that all relative equilibrium points are associated with certain zeros of algebraic equation or?
Well, you know, I mean, we can do it on a line. We can do it on these two orthogonal lines, and that's how far we have got until now. There are some configurations which have no apparent symmetry. And I don't know if we can.
Okay, but the system is Hamiltonian, so
yes.
In a sense it's certain equilibrium or extrema.
Yes. Yes.
So
that may be another approach for finding it, so minimizing energy. Yes.
I think this idea of using polynomials goes back to Tkachenko in the 1960s.
Yes.
Russian.
Yes.
Does anyone here know Tkachenko? I know Hassan talked with him quite often and had met him. Very imaginative character. Steve.
I'm just wondering if you have any indication for large M that you're going to get sort of clustering these nearby solutions.
Yeah. No, I don't know. I've shown you all I know, basically. Yeah.
Yes.
Do you think there is any chance of taking any of this and carrying to the case of imposed external flow, for example, strain? Because this can be, because they are all bounded, they are all confined.
Yeah.
So the strain can always be made as small perturbation in the same spirit that you were doing with epsilon.
Yeah. Yeah. Interesting idea. Yeah.
Any other points? Yes.
When I read Aref's annual review paper, I learned one topological method, one paper which estimates the number of equilibrium states using another method of topology, which is Morse theory. There's a bound. I don't remember exactly. There's a bound how many equilibria you got, fixing n.
Yeah.
And I wonder, how do you compare your AN with the general bound? Makes sense.
Well, I mean, certainly it agrees, but I don't know how good it is. We didn't test that. We didn't test the bound on these configurations here. So I don't know.
You notice if there was some kind of minimum principle that would drive you towards this kind of equilibrium.
Yes. I mean, I think this growing of vortices out is a very nice idea.
Yes.
But you know, it doesn't always work. I mean, sometimes you cannot get epsilon to 1, and there's some bifurcation taking place.
Divergence.
Yes. So, yeah.
Okay, well, I think we come to the end of today's, unless there are any other questions. And I'd like to just thank Morten again. Beautiful lecture.